Hi, in this work we tackle the problem of depth estimation refinement. Given a depth map of a sensor, the task of depth denoising is to increase the signal-to-noise ratio of the depth map, as it is shown on the slide. Consumer-level depth cameras and depth sensors embedded in mobile devices enable numerous applications, such as AR games and face identification. One of the reasons to solve depth denoising problem is the fact that the quality of the captured depth is sometimes insufficient for 3D reconstruction, tracking, and other computer vision tasks. Here you can see some examples of the depth maps captured by iPhone True Depth camera. There are several different approaches to solve that task. Classic filtration-based methods, such as bilateral filtering, are powerful sensor-independent single-image algorithms. Yet, they are not able to work well with noise of such magnitude and lead to oversmoothing and loss of details. A number of works use shape-from-shading techniques with shading extracted from an RGB image to optimize for a detailed depth map. However, these methods require precise alignment of depth and color modalities and rely on strong assumptions about objects' materials and albedo. Several papers use fusion algorithms. Although depth aggregation from multiple frames indeed leads to less noisy surfaces, fusion methods often fail to build consistent geometry, lose details, and produce oversmoothing due to tracking errors. In a recent paper, Self-supervised deep depth denoising, authors propose a method to denoise depth using multiple well-synchronized identical sensors using photometric reprojection loss. We propose a learning-based method for depth denoising of lower quality depth sensors output using supervision of a higher quality depth sensor. We record simultaneous RGB-D sequences with unsynchronized lower and higher quality cameras. Here is an example of a captured sequence. We solve a challenging problem of aligning sequences both temporally and spatially. The created dataset consists of people captured in a variety of poses and lighting conditions, using the shown rig. Our first contribution in the paper is a pipeline for collecting ground truth data for the task of depth denoising. Specifically, we propose a method for temporal and spatial alignment of RGB-D sequences, removing the need in accurate checkerboard calibration and hardware clock synchronization. For each pair of sequences, we seek a shift delta that would align the timestamps of the two sensors so that a simple nearest neighbor search between the timestamps gives us the best mapping. The correctness of alignment is measured based on the spatial alignment score. For each pair of matched frames, we use superpoint detector to extract a set of 2D correspondences, with an optimized and extrinsic matrix T that would transform the higher quality sensor coordinate system into the lower quality one. We use the matched frames to train a deep neural network to transform a depth image from the lower quality sensor to a corresponding depth image from the higher quality sensor, reprojected to the lower quality camera view. At first stage, we train U-Net model on the pairs of frames. After that, we train conv-LSTM over predictions of U-Net using out-of-fold strategy to avoid overfitting. Thus, the model exploits temporal information available in the consecutive frames. Next, we use the proposed method for human body reconstruction and tracking applications. We applied double fusion algorithm to raw true depth data, raw Kinect second data, and to the data obtained by applying the models to the true depth data. As you can see, denoising with our method significantly improves double fusion reconstruction if compared to the result based on the raw true depth data. We also tested our approach using Kinect fusion reconstruction pipeline. Our method provides more details in each frame, resulting in a higher detailed reconstructed geometry. Recently released app In3D, which solves the task of human body reconstruction using iPhone's True Depth camera, incorporates the proposed method to denoise input depth maps. You can find more details about the application at the demo session of the conference. We compared our approach against recent state-of-the-art results. We provide both quantitative and qualitative comparison. Both are shown on the slide. Our approach achieves significant improvements. Here is a visualization of our final results. Thus, we propose a pipeline for self-supervised depth denoising and refinement. We overcome the lack of ground truth data by employing a higher quality sensor and collecting simultaneous recordings. We automatically extract frames captured close in time and do not require the sensor pair to be recalibrated or synchronized. We then learn a deep neural network to denoise the lower quality depth using the matched higher quality data as a source of supervision signal. We experimentally validate our method against state-of-the-art filtering-based and deep denoising techniques. We show its application to 3D object reconstruction tasks, where our approach preserves more details in fused surfaces and leads to better tracking. Thank you for your attention.